Here we have a somewhat complicated implicit function that involves a trig function as well. Let's see what we can do with this. The first thing I want to point out is on the left-hand side we have a product of x and y squared, so we're going to need a product rule. So when we take the derivative of this, and let me write this out, we're going to have the derivative with respect to x of x times y squared plus the derivative with respect to x of y squared times x. That's going to be equal to the derivative with respect to x of the sine of y. Again, I'm applying the product rule on the left-hand side. So this is going to leave me with y squared plus 2xy dy dx. I'm doing some simplifying there. We get 2y times x. We also pick up a dy dx since we're taking the derivative of a y term with respect to x. I'm just reshuffling the order of things there. And what's going to give us the derivative of sine y is cosine y, and we're multiplying that by dy dx. Be careful, we're not multiplying dy dx by y, we're multiplying it by all of cosine y. So we have to be a little bit careful about that. So we can rewrite this as y squared is equal to 2xy dy dx, and that should be negative, plus dy dx cosine y. I'm going to move that dy dx in front of the cosine so we don't accidentally confuse it with the angle. When taking derivatives, we shouldn't be changing angles on trig functions. Angles on trig functions should change only if we use trigonometric formulas or identities that allow us to change them. But our derivative rules won't change angles. We're going to factor out a dy dx, so we're going to get negative 2xy plus cosine y times dy dx. And if we divide both sides by what's in parentheses, we'll end up with y squared divided by negative 2xy plus cosine of y is equal to dy dx. So I took the derivative using my general rules. Anytime I took the derivative of something that involved y, I made sure I got a dy dx. Then I put all my dy dx's on one side of the equation. Anything that didn't have dy dx is on the other side of the equation. Factor the dy dx out. The last thing I use is division to get dy dx by itself. It's not the prettiest looking derivative, but it will allow us to find the slopes of tangent lines anywhere on the original function xy squared is equal to sine of y.